Okay, I think we'll get started. So today we're going to talk about just some silly quantum mechanical model that we will build based on one of the Dirichlet series that we worked on earlier in the course. So we'll call this, we're going to use this particular Dirichlet series with the divisor function, tau, number of divisors, and so we'll just call this the tau quantum model. So what we're going to do is we're going to pretend that we were working on some system, and some quantum mechanical system. We don't have a classical analog, and so we've discovered that somehow this Dirichlet series pops out as the spectral Dirichlet series. So then we work backwards from what we did last time. We'll do a Mellin transform, an inverse Mellin transform, to get the partition function. So we'll take the inverse Mellin transform of this to get the partition function, and that then results in a partition function ranging from quantum numbers 1 to infinity, and the tau sits in as a degeneracy, and then the energy state beta to the n. Now, let's think about this a little bit differently. Let's break this sum up. We know that m times n equals some number, right? We've seen this a lot throughout the course now. So let's break this up into a double sum, m and m and n, and we'll write then this number as this combination of divisors. So e to the minus beta mn. And if we write this out, m1, n1, that's one term here. Then we're going to have m1, n2, m2, n1, m1, n3, m3, n1, and then m1, n4, then both of them 2, and then m4 and n1. So we can explicitly write this out this way as well, as a double sum. And finally, we can talk about a Boltzmann distribution. And often in a Boltzmann distribution, we want to eliminate the partition function and just talk about the ratio of probabilities of being in the excited state versus the ground state. And so in doing that, then this is our expression for that. All right, well, let's write out the quantum states for this, the first few quantum states for this. And what we see here really is steps of 1, because our energy is, so E is just n, En just equals n, so steps of 1. And then Gn is tau. So tau is acting as the degeneracy here. And so, for example, 10, here's the 10. We often used 10 as an example. So number of divisors, 1, 2, 5, and 10. So 4 divisors. So a degeneracy of 4. 12 up here. 12, 2, 3, 4, 6, and 12. The divisors of 12. So 6-fold degeneracy there. Now, one of the things you want to do is count the number of states, or the density of states here, and up to some energy x. So we would sum n up to, or just up to x of tau. Now, we talked about this other way of expressing this, so let's express it as a double sum, and then in that case, the degeneracy here is just 1, because it's being explicitly written out for each possible state. So we're just summing 1 over this. Well, this is a two-dimensional sum, a sum over m, a sum over n, all in steps of 1. So that forms a lattice. And the lattice up here, this is n and this is m. We form a lattice. And we're bound by this equation, right? And so if we solve for one or the other, that's a hyperbola. So interestingly, the density of states are the number of points underneath a hyperbola. So a number of points in a lattice underneath a hyperbola. And so that's what's drawn here. So this would be some constant energy value, and this is the number of states under that. Now, it's well known that these number of points here can be approximated as the form n log n plus 2 gamma, gamma being Euler's constant, minus 1 times n. And this is actually fairly small, and as n gets bigger, you can even the approximation to just n log n. But this is really quite a good approximation, even down to low n's, as we'll see. And then finally, we'll talk about some thermodynamics. We can talk about the total internal energy of the system once we have Q. So it's minus 1 over Q dq d beta, or you'll sometimes see it as minus, and we notice this as the logarithmic derivative, so it is minus log with respect to beta. Then we're going to also show a graph of the heat capacity, which is just the temperature derivative of the total internal energy. And then we won't show graphs, but you could also talk about Helmholtz free energy and the entropy of the system. And just a reminder here, beta is 1 over kT. So beta is the Lagrange multiplier that shows up in the partition function, and it's connected to the physical property of temperature. We'll work in units where K is 1, so we'll be just looking at 1 over temperature. All right, so let's look at some of the graphs here of this and see what that all looks like. Okay, so what we see here is first a graph of tau. So this is simply tau as a function of n here. So n is going this way. So here's our 10. Let's find our 10. So 10 is 4, right? So we've used 10 a lot of as our example. And 12 here, 12 is 6. So this is 12. This was 10 is equal to 4. And so these are basically the degeneracies. Now, as we go along here, we can accumulate then as we count the density of states. So this is the density of states. And again, as a function of n. So what we're doing is we are adding up these terms. So we're adding up tau for n less than some value x here. And I guess this is also, we could also consider that x as well. And the function here then is going to be x log x. On the board I had n log n minus, or plus, sorry, 2 gamma minus 1 x. Okay. And that is plotted as the red curve. That's this red curve. And then the tau is this black curve. And you see the black curve is very jagged because as we step across, we'll pick up a bunch, and then we won't, and then we'll pick up a bunch as we cross through these degeneracy states. Okay, where does this come from? Well, we can think of it as the number of points under the lattice. So at a particular energy, so this is 1 energy, let's say, then we would be counting all of these points. We'd count those up, and that's how much would have accumulated at that point. So that would be, each one of those blue curves would be a point on this graph. So let's say these are the 3 curves. That would be these 3 points, and we'd accumulate more lattice points underneath those. Okay, let's look at the Boltzmann distribution then. So this is going to be pi over p naught as a function of temperature. As a function of state. So this is n, this is n, this is okay. Now this is going to be at low temperature. So this is low temperature. This is going to be high temperature. and this is going to be medium temperature. And so at low temperature, we don't have enough energy to populate those high energy quantum states. So penalized by that low fact that we're at low energies. So the high energy states are more penalized at low temperatures. So we see a decay here superimposed on the degeneracy themselves. Right? So on the tau gets superimposed this exponential decay. And we likewise see that, but less so here at medium temperature and even less so at higher temperature. So the higher the temperature goes, the closer we get to just the tau graph. And in the limit of infinite temperature, then we would just recover the tau graph. Because there's degeneracy, this goes up and down. Again, the ground state is non-degenerate, and then some of the early states, like 12, for example, or well, even like 10, have more degeneracy. So you actually get a probability that's 2.5 times. What is this one? This is probably 6 or something. 2.5 times that of the ground state. Okay, and then finally, let's look at some of the thermodynamics. So this is going to be the total internal energy as a function of temperature. Pretty nondescript here. It looks linear. It's not quite linear, but it is fairly linear, and that's just because we're evenly accumulating these states as we go up in temperature. So we expect the total internal energy to go up in temperature. If the states are coming in fairly consistently, then we would expect that to be fairly linear. If we look at the heat capacity, though, which of course is du dt, then that shows a little bit more action. And although this is very small, this is just so this was like 1170 at the top, and then one, so what is that, 60 on top of 1,000 in terms of the difference. But we do see a slight temperature dependence on the heat capacity there. So that's heat capacity as a function of temperature. All right, we could have done a little bit more. We could have looked at, for example, looked at more quantum mechanically, looked at the states and maybe added some sort of coupling. So we could have said states with the same number of divisors can couple. So we'd add a little piece that would couple those states. Maybe even a more fun thing to do would have been to add some kind of degeneracy splitter or a breaking of the degeneracy. So for example, let's consider state 4, where you would have the degeneracy being 1, 4, 2, 2, and 4, 1. Perhaps we write a function that assigns an additional energy piece that is the sum of those. So we would have 1 plus 4 versus 2 plus 2, and that would cause a splitting. And so those would split into two states and then one state below it. So we didn't do that, but you could certainly go on and do some quantum mechanic based stuff with that model as well. All right, so this was just a silly model. Again, it's representing maybe somewhere in some kind of system you come up with a spectral Dirichlet series first, more naturally, and then you can back yourself out to the partition function. All right, I think that's it for today.